Hello students, matrix algebra. Now a matrix again is a rectangular array of objects. The dimensions of a matrix are expressed as the number of rows by the number of columns. The entry in the ith row and jth column is represented by A sub ij. And the first non-zero entry in a row is called a leading entry. So given the matrix below, identify its dimensions and the leading entries. So let's call this matrix here matrix A. A has 2 rows and 3 columns. So we say that A is a 2 by 3 matrix. Now to identify the leading entries, we look row by row. So looking at the first row right here, the first non-zero entry is this -5 right here. -5 is in the first row and first column. So it's in the 1, 1 position. And when we look at the subscript, the first number is which row you're in, the second number is which column you're in. Be careful not to read this 11. And now looking at the second row, the first non-zero entry is that 1, and it's in the second row, second column, so it is in the 2, 2 position. And we say that A2, 2 is 1. These are the 2 leading entries. Now a column vector is a n by 1 matrix, and a row vector is a 1 by m matrix. Give examples of each. So a column vector might be a 2 by 1. So 5 and 4, so 2 rows, but only 1 column. Often we use capital letters to represent a matrix, but when we switch to a vector, sometimes we switch back to a lowercase letter, but we make it bold. So I might say that this vector, I'll call it V for vector. You'll see either a bold V, something like this, to represent a vector, or if you don't want to do bold, sometimes you see a V with a little arrow on top of it like this. This vector here is 2 by 1, and let's do a row vector. Let's call this row vector W, and let's make it 1 by 3. So 1 row, but 3 columns, 1, 6, -2. This row vector is a 1 by 3 vector. Now a scalar is a 1 by 1 matrix. You can use a lowercase letter to represent a scalar and doesn't have to be bold or have an arrow above it. So a scalar might be a 1 by 1 that's just a 3, 1 row, 1 column. And in such cases, we normally don't put the brackets around it. So all the real numbers, for example, represent different scalars. Maybe here's another one, -5 is a scalar, and a third one, 1/2 is a scalar. Now, 2 matrices are equal if and only if they have the same dimensions and their corresponding entries are equal. Find x and y so that the 2 matrices below are equal. Okay, well, the first matrix is certainly a 2 by 2, 2 rows, 2 columns, and the second matrix is also a 2 by 2. Now, the first rows are already identical. Now we need the second row to be equal, and to do that, let's look at the 2, 1 position, second row, first column. We want these to match, and then we also want the entries in the 2, 2 position, second row, second column, to match. We want 5 to be x has to be 5, but we also want -2 to be x plus y. And since we know x is 5, we know that -2 should be equal to 5 plus y. Subtract 5 from both sides, and that tells us that -7 should be y. So we get x has to be 5 and y has to be -7. Now to perform scalar matrix multiplication, so multiplying a matrix by a scalar, multiply each entry of the matrix by the scalar. So here we have a scalar -3 times a 2 by 2 matrix. And we simply take that -3 and we distribute it to all the terms. So we're going to get a 2 by 2 matrix back. In the 1, 1 position, we get -18. In the 2, 1 position, we get -15. In the 1, 2 position, we get 0. And in the 2, 2 position, we get +6. Now this scalar, this -3, it doesn't matter what side of the matrix it's on. You could put the -3 on the right side of the matrix and multiply that way, and you would still get the same result. Now adding and subtracting matrices is done by adding or subtracting corresponding entries, and these operations are only possible if the 2 matrices have the same dimensions. So again, we have a 2 by 2, and we're adding it to another 2 by 2. A second example will be subtraction of 2 2 by 2s. So in the first case, we're going to do 6 plus -3. We're going to add the 2 1 1 positions, and 6 plus -3 is 3. Now we're going to add the 2 2 1 positions. So the 5 and -1 add to be 4. Now let's add the 2 1 2 positions. 0 plus 7 is 7, and then finally add the 2 2 2 positions. -2 plus 1 is -1. Subtracting is similar. Recall that you should distribute the negative. So when you do 6 minus -3, we're going to get 6 plus 3. We're going to get 9 in the 1 1 position. Then we do 0 minus 7 for the 1 2 position, get -7. In the 2 1 position, we get 5 minus -1, which is 6. And in the 2 2 position, we get -2 minus 1, which is -3. To perform matrix multiplication, follow the process demonstrated below. Okay, so we're going to demonstrate by doing a 2 by 2 times a 2 by 2. And the way this is done is you look to the first column of the matrix that's on the right. Imagine that 1, 2 is dragged out of position and placed here and here. So the 1 is above the first column and the 2 is above the second column of the matrix on the left. which indicates that the number of columns of this matrix should match the number of rows of this matrix. Dropped onto the first row, multiply corresponding entries and add. The 1 drops on the 6, and multiplying you get 6, and then to that we add, and the 2 dropped on the 0, multiplied and got 0. And so that was the 1, 2, which was the first column of the matrix on the right. Then you do that down here to create the next entry in the first column of our product. So we do 1 times 5 is 5, and then 2 times negative 2 is negative 4. So we're going to do 5 plus negative 4, or in other words, 5 minus 4 as the next entry. And this is how we create the first column of the result. So I use the first column of the matrix on the right to generate the first column of the product. Now I use the second column of the matrix on the right and do similar. Drag that 3, 4 out. I'm going to write them over here. Drop them down onto these entries, multiply corresponding entries, and add. So we're going to get 3 times 6 is 18, and 4 times 0 is 0. So we're going to get 18 plus 0. And then finally, we drop the 3, 4 onto the 5 and negative 2. So we get 15 minus 8. And then we close off this product. Now this matrix over here on the right, it is a 2 by 2 again. And now you just want to simplify each of those entries. And 6 plus 0 is 6, 5 minus 4 is 1, 18 plus 0 is 18, and 15 minus 8 is 7. So here's the product matrix. It's a 2 by 2. You'll get to the point where you don't need to write this step here, and you can keep track of the arithmetic that's happening and go straight to an answer. But that takes practice and keeping track of numbers in your head pretty well. Let's look at the product of the same two matrices. So I'm going to take these same two matrices but multiply them in the reverse order. So here it is in the reverse order. And this time I'm going to do the work mostly in my head. I will take that 6, 5. I'm going to write it here. And imagine this 6, 5 dropping down onto that 1, 3. 6 times 1 is 6. 5 times 3 is 15. And then 6 plus 15 is 21. So I get 21 in the 1, 1 position. Now drop the 6, 5 onto the 2, 4. 6 times 2 is 12. 4 times 5 is 20. 12 plus 20 is 32. And there's our first column of the product matrix. And we're done using the 6, 5. Now I'm going to grab the 0, negative 2. Drag them out, bring them over the columns of the matrix on the left, and drop the 0, negative 2 onto the rows. 0 times 1 is 0, and negative 2 times 3 is negative 6. And add those together, we just get negative 6. And then take the 0, negative 2 and drop it onto the 2, 4. 2 times 0 is 0, and 4 times negative 2 is negative 8. And add those together, we get negative 8. So here's my 2 by 2 result when I multiply in this direction. And the first thing that should jump out to you is that the results are not the same, suggesting that matrix multiplication is not commutative. In general, A times B is not going to be the same thing as B times A when you multiply matrices. Also, note that A times B is only possible if the number of columns of A, which is the matrix on the left, equals the number of rows of B, which is the matrix on the right. Find the products below if possible. Okay, so the matrix on the left, this is a 3 rows and 2 columns. So this is a 3 by 2. And the matrix on the right is a 2 by 1. 2 rows, 1 column. Now we want the number of rows of this matrix to equal the number of columns of this matrix. In other words, we want the two interior numbers to be the same. And not only that, but if they're the same, then we know that the resulting matrix will be the outer numbers. So the result will be 3 by 1. Let's go ahead and get our answer now. So we take the 5, 6, and then we drop the 5, 6 onto these entries. 5 times 0 is 0, 6 times 3 is 18, so we're going to get 18 as the first entry. Then we drop the 5, 6 onto the 1 and 5. So 5 times 1 is 5, 6 times 5 is 30, add those together, we get 35. And then we're going to drop the 5, 6 onto the last row. 5 times negative 2 is negative 10, 6 times 4 is 24, and negative 10 plus 24 is 14. And this is our 3 by 1 result. Okay, let's look at the next. This is a 2 by 3 matrix on the left, 2 rows, 3 columns. And we have a 3 by 2 on the right. So because the two middle entries are the same, we know that this product will be possible, and the result will be a 2 by 2. But we're going to grab the 4, 0, 1, bring it over the columns of the matrix on the left, and then drop them down, multiply corresponding entries. So we have 1 times 4, 0 times 2, and 1 times 3, and we add all that together. So we're going to get 4 plus 0 plus 3 is 7. So we get 7 in our first entry. Now take the 4, 0, 1 and drop it onto the next row. So we have 3 times 4 is 12, plus 2 times 0, that's a 0, and 1 times 1 is 1. So we get 12 plus 0 plus 1, that gives me 13 in this position. Now we're going to focus on this 0, 5, 2. Do the same process. So 0 times 1 is 0, 5 times 2 is 10, 2 times 3 is 6. So we have 0 plus 10 plus 6, 16. And now we take the 0, 5, 2, drop it down here. We have 0 plus 10 plus 2, that's going to be 12. Okay, in the last case, we have 2 rows and 3 columns. And the matrix on the right is a 2 row by 2 columns. And so this one, the two inner numbers are not the same. So this product is not possible. And you can see why that's the case. If you took the 5, 0, we would need 3 numbers right here to match the 3 columns here. So we would need 3 rows over here, but that's not the case. So we just say that this matrix multiplication is not possible. A matrix is square if the number of rows equals the number of columns. The main diagonal of a square matrix consists of all entries of the form AII. So A11, A22, A33, A44, etc. form the main diagonal. So in this 2 by 2 example, the main diagonal would be the 6, -2. It's in the 1, 1 position and the 2, 2 position. Now, a square matrix is said to be diagonal if all entries not on the main diagonal are 0. An identity matrix, capital I sub n, is a diagonal matrix with 1s on the main diagonal. So an identity matrix has 1s all on the main diagonal, 0s everywhere else. And the n indicates its dimensions. An example right here, this would be I sub 2, because there's 1s on the main diagonal, 0s everywhere else, and it's a 2 by 2. Now compute the products below. Matrix A, and we're multiplying it by an identity matrix of the same size, so times I2. If it's obvious the dimensions, you don't need to write the subscript on the I. You can just say A times I. And let's see what we get as a result. We're going to take the first column, the 1, 0, and then drop the 1, 0. 1 times 6, 0 times 0, add the results, we get 6. 1 times 5, 0 times -2, add the results, we get 5. Now let's grab the 0, 1 and drag it out over here and drop it down. We're going to get 0 plus 0 here for the first entry in the 1, 2 position, and then 0 times 5, 1 times -2, add the results, we're going to get -2. So our resulting 2 by 2 matrix, notice it's the same thing as the matrix A. So when you multiply a matrix by the identity matrix, it does not change that matrix. A times I will give you A. Let's see if we do the reverse order, if that is still true. So now we're doing the identity matrix on the left times the matrix A on the right. So we're going to grab the 6, 5. We're going to drop the 6, 5 onto the rows of the identity matrix here on the left. 6 times 1, 5 times 0, add the results, we get 6. And drop the 6, 5 onto the 0, 1. We're going to get 0 plus 5, and that gives me 5. Now let's take the 0, -2 and drop them onto the rows of the identity matrix. We're going to get 0 plus 0, so we're going to get 0 for the first entry, and then 0 plus -2, so -2 as the next entry. And so we can see that we get the matrix A back again. So it seems that when you're multiplying with an identity matrix, we do have matrix-matrix multiplication is commutative. And in each case, you get the original matrix back. So in general, we can say that A times I will equal I times A and will equal A in both cases. Now suppose the product of two square matrices is the identity matrix. Then the two matrices are said to be inverses of each other. A will represent one of the two matrices, and A with a -1 power on it will represent the inverse matrix. So look at these two matrices here. Let's go ahead and multiply them. Let's take the 2, -5 and write it over the columns of the matrix on the left and multiply these. So we have 2 times 3 is 6, and then -5 times 1 is -5. Add those results, we get 1 back. Now take 2, -5, drop it here. We're going to get 10 minus 10. We're going to get 0. Now grab the -1 and 3 and do the same thing. -1 times 3, drop them here. We're going to get -3 plus 3, so we're going to get 0 in the 1, 2 position. -1 times 5 is -5. 2 times 3 is 6. Add those results together, and we are going to get 1. We had A times B, and we got the identity matrix back. When this happens, we say that these two matrices are inverses of each other. So we can say one of two things. So we can say B is the inverse of A, or we can say that A is the inverse of B. Now let's see if we take the same two matrices A and B as they are here and switch their order. See if this affects anything. So let's take the 3, 5, 3 and 5, go right there. Then we're going to take those two numbers and drop them down. So we're going to get 6 minus 5, we're going to get 1. And then drop them here. -15 plus 15 will give me 0. Now let's take the 1, 2. 1, 2 drops down here. We're going to get 2 minus 2 is 0. And then we're going to get -5 plus 6 is 1. So we do get 0, 1. So we got that B times A also gave us the identity matrix. And when that happens, we can say that B is A inverse, or we can say that A is B inverse. It doesn't really matter. So this also shows us that when you multiply two inverse matrices, you will get the identity matrix as the product, but also that the product of inverse matrices also commutes. So A times its inverse will be the identity, as will its inverse times A. Now, if it exists, the inverse of a square matrix, A, is found by row reducing an augmented matrix, which is A, next to the identity matrix of the same size, and we're going to row reduce it to the identity matrix on the left. In other words, we're just going to put it in reduced row echelon form. Now, not every square matrix will have an inverse, so it won't always be possible to multiply a matrix by another matrix and get the identity back as a result. That only happens for some square matrices. So we're going to say that this is the matrix A. So I'm going to construct A next to the identity. So I'm going to put 3, 1, 5, 2 I'll put a little vertical line here, and then I'll put the same sized identity right next to it. And this is our A/I. And now we start doing row operations until we get in reduced row echelon form. So my first goal is to get a 1 here. Now I could just divide that whole row by 3, but that's going to introduce fractions, and I'd like to refrain from getting fractions. But I notice that if I double this 3, I'll get a 6, and 6 is 1 away from 5. So there's going to be a strategy here. Let's just double the top row, 6, 2, and 2. Now the reason why that was useful in avoiding fractions is I can do -1 times this row and add it to the top row. So the bottom row we're not changing, but the top row we are. And we do -1 times 5 is -5, add it to 6, we're going to get a 1. -1 times 2 and add it to 2, we're going to get a 0. Now we do -1 times 0 is 0, add it to 2, that's going to stay a 2. And finally, -1 times 1 is -1, add it to that 0, we get -1. So we have the 1 in the right position. Now we want this to be a 0 below it, so we're going to multiply the top row by -5 and add that result down to the bottom row. So we do -5 times 1 and then add that to 5, and that's going to give me 0. -5 times 0 and add to 2, that's going to stay 2. -5 times 2 is -10, add that to 0 will give me -10. And finally, -5 times -1 is 5, and add that to 1 is going to give me 6. Now we're super close already to having this look like the identity matrix. We just need this here to be a 1. So I'm going to now multiply the bottom row by 1/2. So we're going to get a 1 here, a -5 there, and a 3 there. So this tells us that A inverse is this 2 by 2 matrix that we see on the right. 2, -1, -5, 3. This, of course, confirms what we saw up here. The matrix I'm starting with A is the same matrix here I called A. So our goal was to find this inverse matrix. And notice this is exactly what we got down here. Now let's do this middle one. Begin the same way, set this up. So we have 1, 2, 2, 4, and then we put the identity matrix of the same size next to it, and we make this an augmented matrix. We already have a 1 here, so we just need that to be a 0. So we're going to multiply the top row by -2 and add it to the bottom row. -2 times 1 is -2, add to 2 there, gives me 0. -2 times 2 is -4, add that to that 4. Oh, that also gives me 0. And right here I know I'm pretty much done. I'm going to get a -2 next and a 1 next. But once you get a row of zeros in your matrix on the left, it's now impossible to get the identity matrix. This tells us that the matrix up here, matrix B has no inverse. You can also say that B is not invertible, or you can also say B inverse does not exist, DNE. And now we have a new matrix over here. Let's call this matrix C. This is a 3 by 3 matrix. So we put 1, 0, 1, 2, 1, 2, and 0, 1, 2 next to the identity matrix of the same size. And now we're going to do row operations until this side looks like the identity. Well, we've already got a 1, 2, 0 here. We just need that to be a 1, 0, 0. So I need to change this to a 0. Multiply the top row by -2 and add that to the middle row. And we do 1 times -2 is -2. And then add that to 2, we're going to get 0. And now we do 0 times -2 is 0. Add it to 1, that's going to stay 1. And we do 1 times -2 is -2. Add it to this 2, we'll also make a 0 there. We do 1 times -2 is -2. Add that to 0, we'll make a -2 here. And going more quickly, we're going to get a 1 here and a 0 here. Okay, now we need this to be a 0 down there. And we're going to use this leading 1 to make that a 0 by doing -1 times the middle row and adding that result to the third row. Going more quickly here, we're going to get 0 in the first position, 0 below. We're going to get a 2 here, a 2 here, a -1 here, and a 1 there. Now we want this to be a 1 and not a 2. So we're going to go ahead and multiply this whole row by a half. And also I'm going to go ahead and make this be a 0 up here as well. So in one step we're going to get the correct column here at the end. We need this to be 0. So I'm going to multiply this by a -1/2 and add it to this row. And then I'm also going to do 1/2 times the bottom row permanently, so that in the same step we can be done. Okay, so the top row is changing and the bottom row will ultimately change as well. -1/2 times these zeros won't change this 1, 0. But -1/2 times 2 is -1. Add to 1 gives me 0. -1/2 times 2 is -1. Add to 1 will make that a 0. -1/2 times -1 is +1/2 and add to 0. So we're going to get a +1/2 right there. And finally, -1/2 times 1 is -1/2. Add it to 0. We'll get a -1/2 right there. So there's my new first row. And now I'm going to rewrite the bottom row, but cut everything in half. So we have 0, 0, 1, 1, -1/2, +1/2. And so we have the identity matrix I3 on the left, which means that what we have here on the right will be the inverse. So we know that the inverse matrix C will be this matrix here. And sometimes if there's a common fraction in all these, factor out a 1/2 and then rewrite this matrix so that there's no fractions inside of it. So factor out 1/2 from all the entries. So we have 0, 1, -1, If I factor a half out of -2, it's going to become -4. In other words, just double all the entries on the inside now. So here's one way to write our inverse. This is commonly done when there's fractions involved, is factor the fractions out so that you have a matrix next to it that has no fractions. If you take the matrix C and you multiply it by its inverse, you should get the identity matrix back, and this would be the I3. I'll leave it to you to confirm that. The determinant of a square matrix, which is represented by DETA, or by putting A in these appear to be absolute value signs, is a scalar found in the following ways. Now, a square matrix A is invertible, it has an inverse, if and only if its determinant is not 0. So this is going to be an interesting way to determine whether a square matrix has an inverse. Now, if we're doing a determinant of a 2 by 2 matrix, it's rather straightforward. You simply multiply the main diagonal, I'll put a plus here, meaning keep the sign of that, and then you multiply the other diagonal, not the main diagonal, and you subtract that product. So these symbols all mean is you do 1 times 4, and then times a positive 1. In other words, just keep the sign, 1 times 4. And then you do 2 times 2 and change the sign. Or in other words, do 2 times 2 times a -1, and you get -4. And then you combine these. And notice we get 0. Now this determinant is 0, meaning that the 2 by 2 matrix that we see inside here is not invertible. Well, we already knew that because our last example, we tried to find its inverse. Here's that same 2 by 2 matrix, and we were unable to produce an identity on the left, and therefore we know that the inverse of B does not exist. Let's do the 3 by 3 next. Now, for 2 by 2s, you do this crisscross pattern, but for 3 by 3s and larger, you need to do something that's called cofactor expansion. You want to identify the row or column that has the most zeros. That'll keep your computations at a minimum. And I'm looking at the first column or the first row. They both have 1 0. So it doesn't really matter which one I pick. Let's go with the first column. Also notice I did not write the DET in front. I didn't need to, simply because instead of square brackets around this matrix, you put absolute value bars. So when you see a matrix inside absolute value, it represents the determinant of that matrix. And to find this determinant, we're going to do cofactor expansion along the first column. We begin by crossing out the first entry of that column. Let me back up a little bit. We have something called a matrix of signs. A matrix of signs is a matrix that begins with a plus in the top left position, and then it just alternates. And it's as big as you need it to be. And you create this checkered board of signs, and the top left position is always plus. We only really need a 3 by 3 in this case. So the 3 by 3 matrix of signs looks like this. You put this plus minus plus over these entries, you're going to see how that comes into play. Now in this case, since we're doing cofactor expansion along the first column, the only relevant signs from a matrix of signs are the plus minus plus. So when you cross out the row and column containing that 1, now the matrix of signs puts a plus in front of that 1. So we have a 1 in the positive position, so just a positive 1. And then you multiply that positive 1 by the 2 by 2 determinant that's not currently crossed out. Now you move your targeting down to the next entry of that column. So we target that 2, and the 2 is in a negative position. So we're going to say minus a 2, and then a 2 by 2 determinant. Now what's not crossed out is 0, 1, 1, 2. So you write that next. Then we take this shading and we cross out that 0 at the bottom. Now because there's a 0, I really don't need to write this part. It's in a positive position, so we have a positive 0, and there's a 2 by 2 that's a 0, 1, 1, 2. But this 0 coefficient is going to zero out all of this. So we really only have to do these calculations here. So we have 1. I don't need to write the 1. And then we do a 2 by 2 determinant. So we do our crisscross pattern. We do 1 times 2 is 2. And then we subtract 1 times 2. So we do 2 minus 2 here, and we get 0 for our first entry. Now for the next one, we do 0 times 2 is 0. And then we do minus 1 times 1, so minus 1. And then of course you get 0 at the end of the last one. And so our final answer here is going to be a positive 2. So because we got a positive 2, we know that this 3 by 3 matrix right here is invertible because positive 2 is non-zero. Well, that's the same matrix that we did right here, matrix C, which we found its inverse right here. But we could have known that the matrix was invertible from the start by showing that its determinant was non-zero. Now for a 4 by 4, again, you want to do also cofactor expansion. First thing you want to do is identify the row or column that has the most zeros. And I see a tie. I see a column here that has 2 zeros and a row here that has 2 zeros. So it doesn't really matter which one we do. Let's do our cofactor expansion along the second column. Now our matrix of signs would put a plus in this position. So this position would be a minus 1, then a positive 2, then a minus 0, then a positive 0. Now we target the first entry of that column. Now the matrix of signs puts a negative in front. So we have a negative 1 times, and then we write a 3 by 3 determinant of what is not crossed out. And now we move our targeting down to positive 2. So we have a positive 2 times a determinant, what's not crossed out. As we continue to expand along that second column, we get 0 as coefficients for the last two, so we don't need to bother with those last two. We're just going to get zeros. Now what you have to do is figure out two 3x3 determinants. And I'm not going to finish this problem, but you would find out this 3x3 determinant by doing cofactor expansion maybe along the last column. And this 3x3 you do cofactor expansion maybe along the second column. So you have to do more cofactor expansions until you boil it down to a bunch of 2x2 determinants that you can do with your crisscross, like we saw right here. A system of linear equations can be written in matrix form as demonstrated below. So we have 3x plus y is equal to 1, and 2y plus 5x is equal to 3. Our goal is to write this in the following form. Some sort of matrix A, which is going to be a 2x2, times a 2x1 vector of variables x, and will be equal a 2x1 vector of constants. We'll call that vector B. Now keep in mind, when you do such a product, the middle twos match, so the outer twos give you the resulting product. So the result of this product should be 2x1, which is exactly what we have on the other side of the equal sign. So this is a sensible statement. Now the way you want to do this is the matrix A is going to be the coefficients of the x's and y's in order of x then y. So our matrix A, the coefficient of x is 3, the coefficient of y is 1. Now mind you, down below we have to do some unscrambling. You want to put the coefficients of x in the first column, the coefficients of y in the second column. So you have to unscramble this. So the coefficients of x are 3 and 5, and the coefficients of y are 1 and 2. Then we multiply it by a 2x1 column vector of the variables x and y. Then we set this equal to the 2x1 column vector of the constants on the other side of the equal sign. Keep in mind what matrix multiplication does. It would take that xy, it would put it right here and here, and it would drop it down onto the 3 and 1. So we would say 3x plus 1y, which is exactly what we get right here on this side. And then we drop that xy down onto the 5, 2, we're going to get 5x plus 2y, which is exactly what you see right here. And so when you do this multiplication right here, you get these sides of our equations. And then we want that to be equal to this side. And when a 2x1 equals a 2x1, you can set the entries separately equal to each other. And hence we have this system of equations. Now, if the coefficient matrix A is square, so this matrix here, and its determinant is non-zero, which means that its inverse exists, then the system can be solved using A inverse as demonstrated for the system above. Okay, I'm going to first illustrate something we're already familiar with. And that is if I have something along the lines of 3 times x is equal to 5. So this is just a regular equation, no matrices here. And I say solve this for x. Most people would say, well, divide both sides by 3 and you're done. X equals 5/3. But instead of thinking of division, you would multiply both sides of this equation by the multiplicative inverse of 3. You multiply both sides by 3 inverse. Well, 3 inverse is a third. So we do a third times 3 times x is equal to, and this is going to be 5 times a third. And a third times 3 is 1, so we get 1 times x. And 1 is considered to be the identity for scalar multiplication. Multiplying by 1 doesn't change anything. And 1 times x, of course, is just x. It doesn't change, and so we get x equals 5/3. Now, if you have matrices instead, this is how it looks. You have a matrix A times a vector x equals a vector B. You're going to multiply both sides by the inverse of the matrix A, if it exists. So we're going to put A inverse, and you have to put it on the left of each side. So you can't write B times A inverse. This won't actually make sense. This won't be a possible product. Instead, you want to do this product. So make sure you put your A inverses on the left of the left side and on the left of the right side. And now we use the fact that A inverse times A will give you the identity matrix. So you're going to get some sort of appropriate size identity matrix times the vector x equals the inverse matrix of A times the vector B. But of course, multiplying the identity times anything doesn't change it. So the vector x times the identity will stay the vector x. You can find x by multiplying the inverse of A times the vector B. So let's look at our system above. This is our matrix A here in the front. And notice that it's a matrix for which we've already found an inverse. It was this matrix here, and its inverse we've already calculated. So I'm just going to copy it and bring it down to our work down here. So we're going to be able to say that xy is equal to the inverse of A times the vector B. Right, so you can see our structure. We have A times vector x equals vector B. In our next line, we have vector x by itself is equal to the inverse of A times vector B. And now all I have to do is do matrix vector multiplication right here, and I get my xy. So we're going to get xy equals, and then we just have to do this product. Here's the 1, 3. So we get 2 minus 3, so we get negative 1 in our first entry, and we're going to get negative 5 plus 9, which is going to give me 4. And this reveals the solution to the system. X should be negative 1 and y should be 4. If x is negative 1 and y is 4, then we're going to get negative 3 plus 4, which is 1, check. And we're going to get y is 4, so that's 8. And x is negative 1, so that's minus 5. And 8 minus 5 is 3. So we do have a solution. And we found it by converting the system to matrix form, finding the inverse of the coefficient matrix, and then doing that inverse times the vector to get our solution.